Okay, we are on the final questions of the series now, 31 through 33. Number 31 says, what is the most important difference between covalent, ionic, and metallic bonding? Remember that covalent bonding involves a sharing of electrons. So we saw that here. For example, we saw two atoms. This might be a fluorine atom. For example, this might be a fluorine atom. There are 7 valence electrons that are brought to the bond by this atom, 7 valence electrons brought by this atom. But notice that this atom feels as though it has 8. 1, 2, 3, 4, 5, 6, 7, 8. This atom also feels as though it has 8. 1, 2, 3, 4, 5, 6, 7, 8. Because they both feel as though they have 8, they're both following the octet rule, and it's a more stable arrangement than if each individual atom was alone. So, that's covalent bonding. Ionic bonding, and I'll go back now, remember does not involve sharing of electrons. Crystal lattice is formed in this structure, and there is not a sharing, but rather a wholesale giveaway. Sodium, for example, might give away its valence electron, its outermost electron, to the chlorine atom, and so it forms this sodium-chlorine ionic bond. Sodium-chlorine ionic bond. That's the formula unit for that particular structure. And so that is ionic bonding. Metallic bonding. Metallic bonding involves something called a sea of electrons. So the important thing here is that the ability of metals to conduct electricity can be attributed to this sea of electrons, this ability of electrons to traverse the entire surface of the atoms, and that's called the sea of electrons. So that's the major difference. Remember that covalent bonding, the boiling points are fairly, and melting points are relatively low. Ionic bonding, they are higher, and of course the highest melting and boiling points are for metallic bonding. So that's number 31. Number 32 is be able to predict the geometry of a compound given its molecular formula, or given its formula, and I'll ask you to look at the molecular geometry video for that. So that'll take you through number 32. So just go back and watch that video. It's about 9 minutes long. And finally, number 33, be able to distinguish between the various van der Waals forces discussed in class, including dipole-dipole forces, hydrogen bonding, induced dipoles, and London dispersion forces. So let's take a look at those. Okay, so we started then with dipole-dipole interactions, and remember a dipole is simply when we have a molecule which has one side has a different electronegativity than the other. In this case, bromine has a higher electronegativity than does hydrogen. It's higher and farther to the right in the periodic table. So it is a dipole. So dipoles form dipole-dipole interactions. So if you can imagine a hydrogen bromide molecule, or HBr, in a container with a lot of HBr molecules, then the dipoles are going to attract each other. It's a positive-negative or electropositive electronegative interaction. So they're going to attract. That's dipole-dipole. Here's a diagram showing dipole-dipole interactions. So in this molecule right here, we have a dipole. This is the electronegative part here. This is the electropositive part. And the same thing here. Electron negative, electropositive here. And so you see the bonds. The attractive forces here between electronegative and electropositive. Here, electronegative, electropositive, electronegative, electropositive. So attractive forces, that's dipole-dipole interactions. We talked also about induced dipole interactions, and we said that an induced dipole is one in which a nonpolar molecule, like oxygen for example, is induced to have a dipole. Remember, this accounts for the solubility of nonpolar oxygen in water. Water is a polar molecule. It actually induces a dipole in oxygen, and that's how we explain oxygen being dissolved in water. We talked about hydrogen bonding once again. Hydrogen bonding involves 3 atoms, fluorine, oxygen, nitrogen, bonded to hydrogen, right? One of those 3 bonded to hydrogen, and that creates a relatively strong bond between this hydrogen and this oxygen, for example. Electronegative here, electropositive here. It's an intermolecular bond called hydrogen bonding, and it is the strongest of all the intermolecular bonds that we've talked about. And finally, we talked about London dispersion forces. London dispersion forces are really the most, or are the weakest of all the intermolecular forces. They are the weakest of all because of the fact that they involve only transient intermolecular forces. So we have, for example, nonpolar molecules that do not have polarity and do not have induced dipole interactions involved. these molecules transiently form these occasional bursts of electronic activity on one side of the molecule, so that we have an electronegative momentary dipole, electronegative momentary position on the molecule that causes a momentary dipole. And London dispersion forces happen when those two types of those molecules interact with one another. And that's it. So I want to wish you the best of luck on your examination. That's 1 through 33 now. And go through these videos. I hope you benefit from them, and I will see you on Monday. Thank you. Bye-bye.